Hello, how are you? Lucia and Creepypasto, welcome. Nice to see you both. Today we're gonna be solving the weekly contest 363. Let's start with question number 1, sum of values at indices with k set bits. You're given a zero index integer array nums and an integer k. Return an integer that denotes the sum of elements of nums whose corresponding indices have exactly k set bits in their binary representation. The set bits, okay. So here we get an explanation of what the set bits are. These are the ones when the number is written in binary. Here's an example. So 21 is 10101, which has 3 set bits. We get 2 examples, and there are at most let's try to learn something from this stream. So there are at most 1,000 numbers. The numbers are up to 10 to the 5, and k is up to 10, from 0 to 10. All right. So yes, one thing to notice is that when I first read this problem, I thought that the bits referred to the value in nums and not the index. I mean, here it is clear, but I missed that. So yeah, let's keep in mind that the condition is with the indices and not the values. So yeah, so there are very little numbers, so we can just do this by going over all the indices and then adding the value for that index, and here we want to check if the condition is met. And there is a method of int in Python that counts exactly this, the number of set bits, which is bit count. So we can use that in Python. We want that to be equal to k, and we get the expected answers for the examples and accepted. Okay, so that was easy. However, what happens if from the Hamming distance, yeah, cool that you're learning Python. That's good. Maybe you can use Python as well in addition to Java. So that's a good question. What happens if you don't have this function? Well, it's not hard to, so let's write our own bit count function. You have the same one in Java. All right. But let's see how we would do it if we didn't have it. So this is the same thing that you do to convert any number to another base. So we want to know what the digits are while the number is greater than 0. We just see the remainder when divided by 2 in this case, because it's base 2. Here you can use any other base and this will work. And even you can have mixed bases, like numbering systems, like for example with time, when you have 60 seconds and then 60 seconds in 1 minute, and then 60 minutes in 1 hour, and then 24 hours in 1 day. That's another numbering system where the numbers that you use are not the same, but so this is all the same. So here we want to count the digit, right? Because if it's 1, we count 1, and if it's 0, we count 0. And here, nice analogy. You mean by with the time? The time is also a numbering system, yes. So keep it in mind when you are learning new things to know what the general concept is. And here we return this. So now if we use our version of bit count, we should get the same, and we should also get accepted, right? And there is another way to implement this, which is call to learn. So maybe instead, so here we're going over all the digits, right? All the digits in the binary digits. But there's a way to do this, which instead of going over all the digits, you find there is a way to turn off the least significant set bit. And then in that case, you only have to iterate once for every set bit, which is what we want to count. So we add 1, and the way to do that, so don't worry if you don't understand this initially, but the way to do that is this. So notice that we are incrementing res on every iteration, so we are iterating only the number of set bits on n, which could be less than the number of digits, and we get the same answer and accept it. So why does that work? I'm glad you asked. Well, the reason is, so let's suppose that we have a number n, I'm having trouble with my tablet. Let me see. If I can fix it quickly, because it is pretty essential. All right, so I was able to solve it, luckily. So what was I saying? So yes, so we are doing this. We're doing the AND of n and n minus 1. And we know that n is greater than 0. So that means that it must have a 1 somewhere. This is the least significant 1. So that means that to the right, it's going to have some number of zeros, which could be empty if the least significant 1 is at the least significant digit. And then here we have something else that doesn't matter. Let's represent it by this square. So this is n. And then we want to AND it with n minus 1. So n minus 1, it's going to be, so remember when you did subtraction in school, that so you have a 0, and so yes, if you have something like these, all zeros, and you subtract 1. So this one asks for a 1 to the left and to the 1 on the left, and so on and so on. And this becomes a 0. So this becomes 0, 1, 1, and 1. Right? So that means that n minus 1 is going to be this. The dots mean that they are all the same in the middle. And then here, it's going to have the same rectangle. Whatever this is, it's the same in both. So now, when you do the AND, remember that the AND on 0 and 1 or 1 and 0 is always 0. So this means that in the result, everything is going to be 0 here. And then here, we will have, since we have the same thing, this will not change. So essentially, this is what happened. What happened is what I promised, which is that the least significant 1 was turned off, right? And we do this repeatedly, we're gonna get 0. So yes, this is a nice trick. So again, you don't need to use this if you have a library function, but this helps you understand how to think about algorithms, right? The way that I proved why this works helps you exercise your algorithmic thinking. The way that I expressed all the numbers in an abstract way with this group of zeros here, which could be empty, a 1, and then this block. This is a way of thinking algorithmically or mathematically. So yeah, and so notice that here the structure of our solution is just going over all the numbers in the range and checking whether they satisfy the condition. And this is what you have to do in the context. This is the simplest thing that you could do. But can we do something faster? So what if the array was bigger? So an alternative would be to just generate the numbers with k on set bits. So how can we do that? How can we do that? So maybe we can create a function. So yeah, values, that it's going to give us all the numbers from 0 to len of nums minus 1 inclusive that have a k set bits, right? So how can we do that? So let's call this n and this is k. So again, this is going to give us to return return list of values in 0 and n inclusive with k set bits, right? So if n is negative, then there's no element in this range, so there are none. So we return an empty list. If n is 0, then only 0 is within the range. So, but 0 has 0 set bits. So if the set bits are 0, then we return 0 as a response, and otherwise we return the empty array. Otherwise, if n is greater, then we can have the least significant digit can be 0 or 1, right? And we can call recursively for so we can divide the number by 2 and call recursively for the other digits. We consider the least significant digits, we call for the rest of the digits, we subtract, if it's 1, we subtract 1 to k, and if it's 0, we subtract nothing. And so this is going to give us the values and so for every value there, we can generate the next number, the number with the current digits, and that's going to generate all our values. And it works for the samples, and it works. So this is a little more advanced. This is similar to what we do in DigitDP. Digit backtracking. Yeah, kind of like that. I guess you could memorize this. Yeah, you could, because these are all right. So $80 milliseconds, so it doesn't seem super fast here. Well, because the thing is very small, so it's not, doesn't make any difference. So yes, let me share. Let me start sharing my. Oh, so I I had 5 submissions of this. So yeah, let me share this one too. All right. So yeah, so that's a lot for the first problem, but I like to dig in, as you can see. That's cool. So yeah, let's go to Q2. Happy students. You're given a zero index integer array nums of length n, where n is the total number of students in the class. Class teacher tries to select a group of students so that all the students remain happy. So the ith student will become happy if one of these 2 conditions is met. The student is selected and the total number of selected students is strictly greater than nums of I. The student is not selected and the total number of selected students is strictly less than the nums of I. Return the number of ways to select a group of students so that everyone remains happy. And there are up to 10 to the 5 elements, nums. And this is within, the values are within the range of the size. So yeah, so here this might be hard to parse, but notice that in both cases we are referring the total number of selected students. So maybe a way to simplify this, to think about this, is to consider the total number of selected students, right? What if we have that as a number? So there are not that many possibilities. There are 2. So you can select 0. So for example, here we're told that the selected students could be 0. up to 10 to the 5. So maybe we can try all those total numbers and see what happens here. So that means that here the total number of selected students has to be strictly greater than nums of I if the student is selected. So that means another way to think about that is that, and in the other case, they have to be strictly less. So that means that, so now we have a total number of selected students. So the ones that are less than it should be selected, and the numbers that are greater than it should not be selected, right? That's forced. And so then we can see if this is consistent. If we check how many are less than it, the number that is going to give us the number of selected students based on this rule, and it has to be the same as the selected students that we are considering, right? So we need to check if it's consistent, and if it's consistent, then we count it, right? So how can we do that quickly? We want to know if we are going to select K students, we want to know if the K first are less than K. So if we sort them, so let's say, so K is going to be between 0 and len of nums inclusive. That's all the possible number of selections that we can make, right? And then we want to know if it's, so nums of, so if you're going to select 1, so for example, if K is 1, then the first one, the one at index 0 has to have a value that is less than K, right? That's going to guarantee that the first K elements are less than K, right? Because this is sorted. And the rest should be greater than K. And that's going to be guaranteed by that. And in that case, it means it's consistent and we count it. But there is a little problem here that K at the beginning is 0, so here we're accessing to -1, and here this can be len of nums. So in both cases, at the extremes, you're going to have an index out of bounds, but we can do a little trick, which is to have a get function, and if I is -1, we return minus infinity. So in that case, this condition is going to be met always. If I is equal to the length, we return infinity. And otherwise, we return nums of I. And so here, we just use this function. And we're good. Accepted. All right, so one way to think about this so usually you can think about you can sometimes think about arrays as functions. Maybe I'm just gonna explain this, but don't worry if you don't feel it helps. I mean, sometimes it's good to have many ways, many perspectives to think about problems, but maybe for a particular problem, one way of thinking about it is more intuitive for you, is more illuminating, or it's easier to understand. But if you know many ways, many perspectives, then for other problems, you can find the one that works better. So I think it's usually good to have many ways to think about problems. So yeah, let's say this is, so what do I mean by thinking about an array in terms of so you can think about these coordinates as the index in the array, and then the value in the array could be here. This is a point, and maybe this is another point, and here, and so on. So remember that we sorted this function, so it will be monotone. And notice that we are asked, so this is the slope. So what we are looking for actually is points where, so if this point is I, we are checking if this function, let's say this function comes here, if this function is going over the line at this point, which is kind of similar to what it's called in mathematics a fixed point, which is a point that satisfies this equation. So it's not exactly that, because we don't want the function to be the same. We want the function to be greater at the point and less before it. But I think this is a way that you can think about it in a more visual way. So I wanted to mention it. All right, so that is, so the solution is linear. I don't think we can improve it. Well, I mean, no, not linear, because we're sorting. Yeah, I was wondering, because this is also a functional graph. You can think about it because of this condition, and you can. But in this case, the order doesn't matter. So that's usually a very good observation to make quickly, when the order doesn't matter, because in this case we sorted the array thanks to that observation, and then we were able to do this quickly. Notice that here we could do also a binary search to see how many elements are less than k and how many are greater. But we don't need to, because we don't care how many there are. We want to make sure that there are, I mean, we do care, but we don't care if there's more, how many there are. We care we want to know if there are exactly K. So with this condition, we guarantee that they're exactly K. And then with this condition, we guarantee that there are nothing is equal to K. Well, I mean, with both conditions, we guarantee that. Okay. So yes, so that is my solution. Let me share it. And let's move on to question 3. Maximum number of alloys. You're the owner of a company that creates alloys using various types of metals. There are n different types of metals available, and you have access to K machines that can be used to create alloys. Metal type. Okay, so you have stock I units of metal type I, and purchasing 1 unit of metal has cost I coins. All alloys must be created with the same machine. Return the maximum number of alloys that the company can create. Okay, so let me explain. So yes, you have K machines, and the machine has this number of metals, so it needs this many units of each metal to create an alloy. And you also have a stock of these metal types and a cost of each one. And you want to see which of the machines you want to select to maximize the number of alloys that you can create. Without exceeding a budget. Okay, so it's a little long. The numbers are not big in terms of the sizes, so it's up to 100. But yeah, so first of all, so there are only 100 machines, so we can try each of them and get the one that gives that gets the maximum, right? So we can go over the compositions are given. So let's call these compositions because I don't like this name. And for each machine, you have a different composition, right? And we're gonna so let's say mass alloys for composition, and this is going to be our answer. Okay, so now we have one specific composition and we want to maximize. So how do we do this? So there are many ways to do this, but the easiest way. So notice that we have a function. So we wanted to know we have a function that's gonna give us the cost given let's say the number of units, let's call it U, the number of units of alloys that we want to create, and we want to find the maximum U such that this is less than or equal to the budget. So that means that there are going to be some small use. For example, use 0 is going to have cost 0, so that's going to be true. This condition is going to be true. So this is a constant, right? And once we are increase the function, at some point we're going to exceed the budget, and so the condition is going to be false. So this is a monotone function, right? We get true, 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 and at some point we get all falses all the time. So given that it's a monotone function, we can do a binary search to solve it, right? So we just need to have a way to compute the cost. So let's say that we have a way to compute the cost. So low is 0. So for 0 alloys, we can do it. And let's say that high is initially 1. So we want high. So we want the cost of high. Well, cost is it's an array, so let's call it get cost. So so while the cost is under the budget, we want to increase it exponentially. So this is a common technique in dynamic programming, just to find the in binary search, just to find an upper bound. So notice that here at this point we have this invariant. The invariant is that the get cost of low is less than or equal the budget, and get cost of high is greater than the budget. So high is bad and low is good, right? And why is this true at the beginning? Because we made it so while the cost of high was within the budget, we kept increasing it. So when this finishes, this condition will be true. And we are going to maintain this condition every time, but reducing the range by 2. And how do we do that? We just get the midpoint and we check the condition with the midpoint. And okay, so if this is true, then low has to be equal to mid, so that we keep our invariant. Otherwise, high has to be equal to mid to maintain our invariant. And when do we end? When the difference is 1, which means that they will be consecutive, and that means that low is going to be the maximum value for which we haven't exceeded the budget, right? So that is our standard. So now we have to implement get cost of we call this U, the number of units. So for that, we want to go over all the metals, right? All the metals, and for each metal we have the composition of this metal, how many we need, minus the stock, but we need how many we need per unit. So we need to multiply by the number of units, And here, if we have more stock, then the number of units is going to be negative. So, but we want to keep it non-negative, so we use the trick of maths of 0 and the value. So this is going to give us the number of units that we need, and their cost is given by cost of I, and we add up for each metal, and that's going to give us the cost. So this should solve the problem. Composition. Where am I using? Oh, here, compositions. Yeah, thank you, Lucia. All right. So accepted. Okay. Okay, that's good. So yeah, this is I think it's the intended solution, the expected solution. It's the simplest way. But another way to solve this without binary search. So let's think about our cost function. So it was a sum. So this is how you write sums in math with the sigma. It's the sigma function, right? And capital. Anyways, so we want this I for the metal, and we have the maximum between 0 and what? And it was so this is the cost of U units, and we wanted to multiply U times the composition. Okay, so here we have so this is cost and this is composition of I. Well, here we use C sub I, and we wanted to subtract the stock of I. This is going to give us how many units, and then we, oh yeah, this is, so I need more letters, so I have a lot of collisions in my names. So this is, how do we call this? I don't know, B is, and this is the cost, and let's call this just f of function. Anyways, so, and we want this to be less than or equal to the budget. Okay, so what's the big deal? This is one function, a function of one variable, and we have an inequality. Why can't we solve it? Like the simplicity of the code. Oh, let me share that one. The simplicity of the code. Thank you, thank you. Yes, let me share it, because it's not going to be that simple now when we remove the... Okay, so so what do we do here? So why is it hard to solve this equation? or this inequality, if you will. Well, the thing is this pesky max function, right? This function is hard to deal with, but how do we deal with it? Well, so you can do case analysis to get away. So here we can think about, so there are two possibilities. This one is the maximum or this one is the maximum, right? So it's going to depend on this, right? On whether u times b of u minus s of I is greater than or equal to 0. So if this inequality is true, then we can remove the maximum and we can keep only this, right? So how do we solve this in terms of u? So we add si on this side, and then we divide, and we end up with this. Okay. So this means that if u is greater than this number, this ratio, then we can remove the maximum and just keep this, which is easy to work with. The problem is that we have n of these maximums. So how do we deal with that? So we're gonna have a condition for each one of them, right? So we're gonna let's say that they are ordered, that these ratios are in order. So S0 is gonna be the smallest one, and then we have S of one, and so on. And finally, we have this. So bear with me here. So let's say that we have a u in this range, right? Between these two. That means that this u, which is within this range, is going to be less than this, and that all of them, except for this one. So if u is less than all of those, then this is going to be negative, and all the terms are going to be 0. So what do we do with this? Okay, so eventually we're going to have a condition like this. Thanks, Creepypasta. See you tomorrow. So eventually we're gonna have a condition like this for some k, because for some values this is going to be 0, like we said here, but some of them are not going to be 0. So once we have this, we can solve it by having these expressions. So here we multiply by this, so we manipulate this thing, and here we have S of I and C of I, right? And we do the same that we did here. We're going to have this S of I, C of I, plus B, and here B of I, C of I, right? So here we know what the we were able to have U isolated. So if we do this calculation, we can find the upper bound of U. But like we said before, we need to take into account all the ones that are zeros, which are going to be the ones that are greater than U. Okay, so how does this translate to code? Okay, so we delete this, and we want to sort, we want to get an order that depends on the those ratios. So this is how we do this. We want this to depend on the stock of I divided by the composition of I, because this is what we wrote here. The stock of I, and B we call the composition of I. And we want them from larger to smallest. And then we're going to keep the suffix of the stock. So we want these numbers, the sum of all of them, of the stock times the cost, and the sums of the composition times the cost. And initially we want them, we want to sum all of them, and then we're going to be subtracting. So this was the stock of I times the cost of I, and then the same thing for the composition of I. Right. So initially we could have that so yeah, let's start with this, and for I in order, we want the lower bound to be the CL div, the CL division of the stock of I. And what is that? Well, CL div of A and B is just A plus B minus 1 divided by B. So that's going to give us the division rounded up, the ceiling. And then we want the high upper bound to be what we wrote down there. So the high upper bound is going to be the minimum of the two upper bounds, and we want to know if it is consistent if there is anything inside the bound, and in that case we will update the result, and here we want to update the suffixes. We want to subtract what we added. And we want to update this, which is this without the ceiling, because in this case it's going to be an upper bound, so in that case it has to be a floor division. And there is one catch, which is yes, it could be that we have a number of elements which is less than all of them. So in that case, oh, so we are not returning the result. So what is the mistake here? So we are returning infinity. So that means that we are dividing by 0. Composition cannot be 0. So let's say that we remove this. So when is this getting? Oh, yeah, this is minimum. Yeah, that's a mistake. All right. Okay, so that was not easy. Yeah. Yeah, so this is like, I know it's not a full explanation. But I gave you the rough sketch, so if you're interested, you can dive into it, and maybe you can ask questions in the Discord. I'm happy to go over the details if you are interested. Of course, you don't need this. So yeah, this is a disclaimer, usual disclaimer in my streams. So my goal is not to get accepted for the problem or to get so here in the stream I'm not trying to so I am explaining what's the best strategy for a contest, but here I want to dive into alternative solutions, alternative problems, and so on that maybe are not directly applicable to this contest, but they help you have a wider and deeper understanding. And so in the long term, it helps you understand better and do better at contests also. So yeah, so that's my disclaimer. So Q4. Maximum element sum of a complete subset of indices. So a set of numbers is complete if the product of every pair of its elements is a perfect square. Every pair of its elements is a perfect square. So yeah, this one is a little hard to understand at first, but then I think it's clear. Because again, it's a subset of indices, but the element sum is the values in this array corresponding to those indices, and we're asked to return the maximum element sum of a complete subset of the indices set. Okay, so remember, complete means that you can pair them, so every pair has a product that is a perfect square. Okay. So this is more of a number theory. So the solution is not, the code is not a big deal, but you need to understand a little bit of number theory to get it. Well, not much. So there is one thing that it's called the fundamental theorem of arithmetic, which is I think it's all you need here. Let me share this, which says that every number, every integer can be factorized into prime, and that factorization is unique. So primes are like the atoms of the integers, in a sense. So why do we care about that? So yes, another way of saying that, so we have an integer, and we can always express it as a prime 1 to the e1 and so on, and prime k to the e sub k, right? So for example, for 6 you have 2 to the 1, which is prime, and 3 to the 1, and for 12 you have 2 to the 2 times 3 to the 1, and so on. And another way of writing this, more programmer way, if you will, is like this is like the same operation. Instead of a sum, it's a product. So from, let's say this is I from 1 to k of b sub I and e sub I. All right, so why does this matter? Well, that's a good question. So the first observation here is that for a number to be a perfect square, all the exponents of the primes in the prime factorizations must be even, right? And that is that means that if you have a number n that is p1, but so the same as that, but you have a 2. You have a 2 here, which means that they are even. So that means that you can write it this way if you follow the rules of exponents. So it's all of this squared, if I'm not mistaken. And so now we can think, in this case, in this problem, we are asked to multiply pairs. So every pair has to be a squared when they are multiplied. Their product must be a squared. So again, how do we represent products in terms of primes, factorizations? Well, the answer is that the exponents are added. So here, for example, if we multiply 6 and 12, so if we multiply 6 and 12, we're going to get 1 plus 2 and 3, 1 plus 1, right? Because these are the exponents. And we can do this way. So now we want to know, because every exponent must be even in the product. But we have just said that the exponents get added. So when is an addition? So if we have exponent 1 plus exponent 2, this is a 2, we want to know when this is even, right? Which is it's equal to 0 mod 2. And this is true only when they are both 0 or both 1. They are both even or both odd. That's the only case where you get a 0 here. If you have a 1 and a 0, or vice versa, because the addition is commutative, then you'll get a 1. You'll get an odd number. So that means that for every prime, the parity of the exponent must be equal in both numbers that we're multiplying. So that is interesting. That means that if we only represent the numbers as their prime factorization, but instead of having the opponent, we get the exponent mod 2. This is going to represent, so for example, for 12, so 2 mod 2 is 0, and 3 and 1 mod 2 is 1. So, and this is 1, of course. So that means that we are going to represent 12 as 3. And why do we do that? Because if we get another number that also has that representation, for example, 27, which is 3 to the 3, which we are going to represent as the prime up to the this mod 2. So that means that 12 and 27 have the same representation that we just devised. So that means that 12 times 27 must be a squared. So let's see. 12 27 so it doesn't, so no, it's not. So wait a minute. So I said this is 3, this is 3 times 3, 9 times 3, 27. So this is 2 to the 2 times 3 to the 1, and it's multiplied by 3 to the 3. So this is going to be 2 to the 2 times 3 to the 4, and this is so it is. So this is 9 squared and 2 squared. So it is 18 squared. Oh, it is. Yeah. But yeah, they are not saying what it is, that it is a squared. But that's because Wolfram Alpha is dumb, not us. No, I'm just kidding. All right, so that means that if we factorize the numbers and we substitute the exponent of the prime by the exponent mod 2, then we'll have a representative of that number, and all the numbers in that class can be paired between them, and when you multiply them, you'll get a square. So that means that we can group them all and use the maximal group to maximize the sum that we're asked to maximize. So we need to find a way to factorize the numbers, and the numbers. So the numbers that we care about are remember, they are the indices, and the indices are up to 10 to the 4. So that's not a big number. So let's call this, let's do a and the numbers are 1 based, the indices. So this is the maximum number, and so this is standard code, but don't worry. So this is the maximum value that we care about, and initially, so we want to, so factor is going to give us a prime factor of the number, the index, right? So initially, initially every number is going to be their own factor, and we are going to, so this is the standard. If the factor of p is p itself, it means that p is a prime, and so we go over all the multiples of p, and we set their factor as p, right? All right, so this is going to give us our factoring sieve, and then we can factorize a number. So while the number is greater than 0, so 1 prime is given by the factor of m. So while it is divisible, we divide by it, and we want to count the number of times. So let's call this e, which is what we use there, and that's the exponent. And let's yield this. So this is the prime, and this is the exponent of that prime. So now we have a factorization. This is fast, and we want to use this as a key. Like we said, this is going to be a key of the group. This representation that we explained here, that we'll use only the mods of the exponents, let's call it the key of n. So how do we compute the key of n? Well, we factorize n, and for every prime and its exponent, we are going to keep the prime only if e is odd. So this is going to be our representative of each number. So now we go over all the indices, and the key is this. So we're gonna group then let's use a counter because we're gonna add up there. So the groups for the key, we're gonna add the corresponding value, and then we're going to return the maximum of the group's values. I'm probably not adding something here. Time limit exceeded. So here I'm adding 1. What are the groups in this case? So we're grouping the indices using their prime factorization, but replacing the exponent of each prime by the remainder when divided by 2. So that's going to guarantee that we group together numbers that when they are paired and multiplied, the result is always a square. So I think with your name you should understand this. I would no, I'm just kidding. So where is my loop here? So I'm dividing So I don't know. I'm gonna print something. I'm gonna print something to see what's going on here because I don't see it. Okay, so it seems to be the problem right here. So usually the problem is that I'm don't increment p, but I am incrementing p. So isn't this... What's going on here? So is this is there a collision? Okay, so it's not here. Oh, it's greater than 1. Yep. Anyways, there we go. Accepted. All right. Infinite loop somewhere. Yeah. I knew it was an infinite loop, but I did not catch this, and I was a little thrown off by the fact that it wasn't printing. But I guess it depends on the flash, whether it's flashing or not. Anyway, so yeah, that's it. It's been almost an hour and a half, so I think that's it for now. Thank you, Lucia, for the support. I hope you learned. I did learn a few things, so see you in the next one. Bye bye.